Hi everybody, welcome to your first video lesson in physics. This lesson is Measurement Basics. A couple of things before we start. Number one, you can go to Chapter 1 in your textbook to get some more detailed information on some of the things that I'll be talking about in this video, so your textbook is a good resource. Secondly, you should answer the worksheet questions as you watch this video, and you should pause the video as you're answering those questions, and that way you'll get the most out of this. Okay, so let's get started. Just to give a motivation here, it can really be said that one of the most important skills of a scientist is to make measurements. Scientists make measurements so that they can test their hypotheses and form theories. And so this video is going to be about the details of making measurements. We'll start with the definition. A quantity is any property that can be measured. And what you need to understand is that every quantity must have two ingredients. It must have a magnitude, or a size, and it must also have units, and those units express the dimensions of the quantity. So if you think about your kitchen at home, there are plenty of examples that are kind of non-science examples of quantities. For example, in your refrigerator, you might have 3 gallons of milk. The statement 3 gallons of milk is actually a statement of a quantity. It's the quantity volume. And the magnitude of that statement is 3, and the units would be gallons. So if you have 3 gallons of milk in your refrigerator, that tells you something about how much milk you have. Now notice, if your mom asked you how much milk is in the refrigerator, and you open the door and you told her, well, we have 3 of milk in the refrigerator, I think that your mom would be kind of confused, because you haven't fully specified the quantity. You've only given her a magnitude. And you need to specify units in order for that magnitude to have meaning. In physics, there are 3 quantities which are fundamental in this field of mechanics. So mechanics is what we're studying this semester. Mechanics has to do with forces and motion and objects. The names of the 3 quantities that are fundamental are length, time, and mass. And we're going to be seeing these again and again throughout the semester. They are fundamental quantities because they really cannot be broken down into smaller things or simpler things. Now, these 3 quantities have symbols that are used in many formulas. L is for length, T is for time, and M is for mass. Those are the symbols that show up in formulas involving those quantities. Those quantities also have SI units. The SI units are the meter for length, the seconds for time, and the kilogram for mass. And it's important not to confuse the abbreviations for the units with the symbol for the quantity. So for example, if I ask you for the symbol for time, you would tell me T. If I asked for the units for time, you would tell me S for seconds. Now, of course, there are more than just 3 quantities in science, and oftentimes the quantities are built up from the fundamental quantities. So, for example, if I showed you a rectangle that was 3 meters long by 2 meters tall, and I said, find the area of the rectangle, I'm hoping that you would pretty quickly figure out to multiply those 2 numbers to come up with the area. Area is an example of a compound quantity, and you would hopefully tell me that that rectangle has an area of 6 square meters. And the point here is that area is a new quantity which is actually built up from length multiplied times width. Width is in fact just another length. And so area is compound because you're taking 2 lengths and multiplying them together. One thing to note here is that when you state that answer, remember that you're telling me that the area is 6 meters squared. You're not just saying that the area is 6, because you need to tell me both the units and the magnitude. And you'll notice that the units themselves, for length, multiply. So in this particular example, the units follow the formula. 3 meters times 2 meters gives you 6, and then the meters go to meters squared. And in general, the units will always follow the formula. and you can use the formula as a guide. Sometimes in science we also talk about the dimensions of a measurement, and the statement here is that the dimensions in the units must agree. So probably the best way to explain dimensions is just to give some common examples. If you take for example the quantity that we call mass, that quantity is measured in the SI units of kilograms. Now the dimensions of mass, we say, would be mass itself. It sounds a little bit repetitive, okay, but that's kind of the starting example. If you take a different example like speed, speed is a quantity which we measure all the time when we're driving in a car. That could be measured in SI units of meters per second. We would say that the dimensions of speed are the dimensions of length divided by time. Notice how we've kind of taken the two fundamental quantities and we've expressed speed as a ratio of those. Some other examples here that are for compound quantities. Area is measured in square kilometers, for example. It has dimensions of length squared. Think about the example we just did in the last slide. Density might be measured in kilograms per cubic centimeter. It has dimensions of mass over length cubed. Could you say that the dimensions for density were mass over volume? Yes. But if you break it down into fundamental dimensions and fundamental quantities, you could say that volume is the same thing as length cubed. Alright, the second part of our presentation today is going to cover the ideas of accuracy and precision. And I know that you've learned this already in other science classes, so I'll go quickly and give you some examples as you're working along. Let's start off with accuracy. Accuracy is the closeness of a measurement to an accepted value. This is the definition of accuracy. And accuracy is judged by percent difference. So let's think of an example of accuracy. So here's the example. Let's say that you buy a bag of marbles, and the bag has 100 marbles in it. You take the bag, open it up, and you count the marbles. But when you're counting, you make a mistake. You miss 2, and you only count 98. So the bag actually has 100 marbles, but when you count, you're only counting 98. We would say that the accuracy of your counting is not 100%, because you're off slightly. There's an error. And the formula that's used to calculate this is a percent difference formula. And generally you take the measured value minus the accepted value, and you divide by the accepted value, and you multiply by 100. In this example, I measured 98 marbles. I know that there are 100 marbles in the bag in reality, and so that 100 becomes my accepted value. And when you calculate through, you would say that your counting is 2% below the actual value. So that 2% gives you an idea of your accuracy. Now, if you gave the same bag of marbles to a small child, their accuracy may be quite worse. Because maybe they're not as patient. Maybe they count, 15% below. Or maybe they lose track and they count a certain percentage above. That accuracy is telling you how close your measurement comes to what is the actual true value. Now, at this point, you can refer to the worksheet, and I'm going to have you calculate some examples of percent difference. Yes, you can use a calculator, but I'd like you to kind of think about what you're doing, and after you've answered each of these things, I'd like you to express it as a percentage and use the words above or below. Sometimes students ask about plus or minus. That's okay, but I think if you always state the percent difference as a positive and you use the words above and below, it makes it very clear. Okay? So for example, in this first calculation, you measure 1.5, but the accepted value is 1.3. So you would state a certain percentage above the accepted value. So go ahead, pause the video, solve these problems, and then I'll flash the answers up in just a second. Okay? Okay, and so these are the the actual answers here. And notice I've just used the words above and below and not plus and minus. And it should be pretty clear what that means. Okay, so we've kind of covered that accuracy is the closeness of a measurement. The second aspect of measurements, which is important, is the exactness of the measurement itself. And this is different. It's not the same thing as the accuracy. And I'm going to illustrate that with several examples. First of all, precision can be determined by two different factors. The precision may be determined by the variability in the quantity that you are measuring. And the precision may be determined by the least count of the measuring device that you're using. Now, it's not one or the other. It's typically both of these have some play in determining precision. Usually in our class, though, we'll find that the second factor is the most often, it's the common culprit in precision. Okay, so I'm going to give you an example of each, and then we'll see what do we do with this and what does it mean. So let's think about, first of all, that precision is really can be thought of as the variability in the quantity that you are trying to measure. So let's say, for example, in this class, every day of the week we make a table, Monday through Friday. And every day of the week we count the number of students wearing gym shoes through the class. And these are the numbers we get. So you can see there's some variation here. On Monday we have 12 people, then 15, then 9, then 11, then 13. Okay? Now we're going to assume that my counting is 100% accurate. Okay? So that I know that I've got 12 people wearing gym shoes on Monday. So the question is what's this data telling us? It's telling us that there's some variability in what I'm trying to measure. I'm not always going to have the exact same number of people wearing gym shoes every day. And this is really relating to my precision. So, a reasonable thing to do would be to calculate a mean value by adding up those numbers and dividing by 5. And I could say that on average, my mean value would be 12 students a day wearing gym shoes to class. Okay? And notice that mean only happened on one of these days, on Monday. In fact, it doesn't have to happen on any particular day. But 12 happens to be my average. Now if I look, it looks like I also have some variation here, plus or minus 3. Because on Tuesday I had 15 people wearing shoes, which is 3 higher than my mean. But on Wednesday I only had 9, which is 3 less. And so the point here is that if I say that my mean value is 12, the digit 2 is kind of estimated, and it has some uncertainty, because it can be high or low by some plus or minus value. Now there are a lot of statistical ways of dealing with this. You can talk about standard deviation, for example. I'm not going to get into that in this presentation, but I'd like to at least make the point that sometimes when you're trying to measure something, it moves around on you, and there's a range of values that would be acceptable. Okay, so sometimes we'll see this in labs that we do in class. Now, the other source of precision, or limitation to precision, is the least count of the measuring device. Now, I'm going to give you a couple of moments here. You might want to pause the video, and on your worksheet, I'd like you to kind of estimate the length of the pen. But you can only estimate it using the ruler that I give you. Okay? So if you would like to pause the video now and answer some of those questions, then we'll come back in just a second and go through. Okay, so go ahead and do that now. Okay, so let's see how that you did on that. So the question is how long is this pen? Well, you really have to kind of estimate here. It would be you know that it's going to be more than 10 centimeters and less than 20. But it would be ridiculous to say that the length of the pen is 12.25349 centimeters, because you simply don't know from this ruler that level of precision. So probably many of you estimated a length of about 13 centimeters. Okay? Maybe some of you estimated 12, maybe some estimated 14. That's okay, but the point is that digit in the ones place, it's estimated. Now if I gave you a different ruler but the same pen, and I said how long is the pen this time, you can see that now everyone is going to agree the length of the pen is between 13 and 14 centimeters. And now people are going to be estimating the 10th place. And the message here is that the last digit in a measurement is always estimated. And this is what we mean by an error, a measurement error. And I expect that when you're given measurement devices in class, like a stopwatch or a ruler, that you will always try to read between the lines and estimate the last digit, because that's the best that you can always do. And you can't really do much more than that, but it's important that you try to estimate that last digit. Okay, and so this is the second way that precision can be limited. It's by the least count of the measuring device. Alright, so big slide here with lots of things in red. I'll just read through it here. When you're recording a measurement, there are rules that guide the number of digits that you write down. Okay, these rules, of course, have to do with the precision. I gave you a handout today that summarizes these rules. These are the rules of significant figures. And so I'd like you to try out some of those practice questions. I know that you've learned and practiced these rules in chemistry. Generally, in this class, we're going to be using 2 to 3 significant figures for measurements and calculations, just kind of as a rule of thumb. So at this point, I'm going to pause the video. I'd like you to do the examples, and then when you're done, you can check your answers on the slide. Okay, go ahead. Alright, and then you can pause this slide in the video to check out your answers and see how you did. Hopefully you did well with that. There are a few other questions here that I'm going to let you finish up with on accuracy and precision and how they might be related. Oh, I'm sorry, how they apply to these different examples. If you think about an archer shooting arrows into a target, the archer might achieve different patterns. In the first case, he puts everything right in the bullseye. In the second case, he's very close together, but he's kind of off the mark. In the third case, the archer is shooting kind of all over the place, but on average, the marks are kind of coming close to the center. So if you could go ahead and try to make some prediction about accuracy and precision, if that makes sense to you. Okay. And so, a way of describing these particular patterns would be to say that the first example is highly accurate because all the marks are right on the bullseye. And it's also high precision because the marks are close to each other. There's not a lot of variation. In the second example, the accuracy is low because the archer is missing the target, the bullseye, but the precision is high because the shots are all very close together. This might be someone with bad vision who consistently aims low and to the left. And the last example is actually, maybe surprisingly, high accuracy. Why is it high accuracy? Well, it's high accuracy because even though the points are spread around, if you were to average those points and find a mean, they would happen to be on the bullseye. So the accuracy of these shots are actually high, but the precision is quite low. Okay, if you look at the group of these shots, the accuracy is high, but the precision or the closeness of the shots, the exactness of them, is low. Here's the last question, and again, it's very important that you answer this first and then listen to the explanation. How do these clocks differ in precision and accuracy? So what are these clocks? Well, these clocks are 3 clocks that I bought from the same store. They're exactly the same, except I just took the 2 hands off of the first clock, I took 1 hand off the second one, and I left all the hands in the third one. And I basically started them all at the same time and let them run. So these clocks are measuring time, of course. The question is how do they differ in precision and accuracy? So please, you think about that and answer it. And then when you're done, I'll tell you how that might work out. Go ahead. Whoops. Okay, so the surprising answer to this is that all 3 clocks essentially have the same accuracy. What? Students get confused by this. Why can all 3 clocks have the same accuracy? Well, let me ask you this. If you were to let these clocks run for 12 hours, wouldn't all of the clocks, small hands, they're hour hands, basically advance by 12 hours? They would agree. In other words, the shortest hand on each clock is always going to be perfectly like the shortest hand on the other clocks. They're always going to be in the same orientation, no matter what. Okay? So the clocks themselves all keep great time. They're all very, very accurate. The precision, however, is quite different. The least count of this, let's start with the bottom clock. The least count on the bottom clock is going to be 1 second, and that's given by the seconds hand. Okay? Those are the clocks that oftentimes we have in our homes. That's highly precise. The middle clock has a least count of 1 minute because it has the minute hand. So it's a little bit less precise. And the top clock has a least count of 1 hour. Okay? Now, of course, you can estimate a fraction of an hour, but the least count is actually just 1 hour. So the precisions of these clocks go from the high precision down on the bottom clock to less precision in the middle to low precision in the top. And the accuracy is the same for all, just to summarize that. Okay, so that pretty much wraps up the lesson. I hope that you thought about some of those examples before checking the answers. Just to summarize what we said about precision and accuracy, remember, precision is the exactness of the measurement, and accuracy is the closeness of the measurement to the accepted value. Tomorrow in class we'll do some more practice with that, and if you have questions, certainly bring them along. All right, see you later.